When we are doing u substitution with definite integrals, we have to be a bit careful because the limits of integration that we're using are always limits of integration for x. So let's look at an example of how we can carefully integrate over x limits while using u substitution. So let's say we want to find the definite integral from 0 to pi over 4 of sine 2x times cosine 2x dx. Well, we can see that everything is in terms of x. So the limits of integration we're given here are from x equals 0 to x equals pi over 4. We are going to set a value for u and substitute u, but when we go back and evaluate the integral at the end, we do need to remember that the limits we're given, pi over 4 and 0, are for x, not for u. So let's let u equal sine 2x, then du equals cos 2x, that's our outer derivative, times 2, using the chain rule. So that means that du over 2 equals cosine 2x dx. Sorry, I forgot my dx's there. Okay, so we're going to replace cosine 2x dx with du over 2, and we're going to replace sine 2x with u. This is the integral from 0 to pi over 4, remembering this is x we're talking about, equals x of 1/2 u du. And so this is u squared divided by 2 times that 1/2. So we have u squared over 4. And we're going to be evaluating that from x equals 0 to x equals pi over 4. Well, how are we supposed to evaluate that if we have a u and not an x? Well, we're just going to have to replace our u with x again. So we get sine 2x squared over 4. And now we're going to evaluate that from 0 to pi over 4. And this time it is in terms of x. So we can go ahead and plug our pi over 4 in. So we can do sine of 2 times pi over 4. And then that whole thing squared over 4 minus sine of 2 times 0. Then all that squared over 4. And we are going to then evaluate. So 2 times pi over 4 is pi over 2. Sine of pi over 2 is 1. 1 squared is 1. So this is 1/4. And sine of 2 times 0 is sine of 0, which is 0. So this is, and 0 squared is still 0. So 1 over 4 minus 0 over 4. So our final answer for this integral is 1/4. Okay. So the really key thing about all of this is that when we are doing u substitution, the given or original limits of integration are x values. Okay, so make sure you only substitute them in for x's. Okay, so for this method, let's go back here and take a look. We have this example 1. Let's call what we've done here method 1, which is that our limits of integration are in x, everything stays in x, which means we use our u as part of the process, but then we get it back to looking like an x just like we would have done if it were an indefinite integral. However, there is another option, and sometimes this can be a little bit easier depending on what you have to substitute back in. If you don't want to do something that is, if it's a very complex function, sometimes you don't want to have to do the substitution and then evaluate something that's complex, because often the function you get in terms of u is going to be simpler than the function you get in terms of x. So let's take a look at method 2. So let's have an example 2. We're going to take the integral from 1 to 2 of x cubed plus 2 to the 5th times x squared dx. Okay, and so this, of course, is x equals 2 and x equals 1, because that's what we're given. So we're going to do our substitution, but we're going to do a little bit extra. So first step is we'll let u be our inner function, which is x cubed plus 2. So du is equal to 3x squared dx. So that means we see an x squared dx, but not a 3x squared dx. So that means x squared dx is du over 3. So we're going to be substituting there, but we're not going to stop there. What we are going to do is we're going to actually find what the upper limit is before we integrate. So this is sort of like doing that calculation first. So we're going to evaluate u at x equals 2. Well, u is x cubed plus 2, so this is equal to 2 cubed plus 2, which is 8, plus 2, which is 10. Okay, so this is our upper limit of integration, and our lower limit, we're going to evaluate u at 1, which is 1 cubed plus 2, which is 1 plus 2, which is 3. And so now what we're going to do is we're going to rewrite our integral, except this time we're going to actually change what the limits of integration are and give the u limits of integration. And when we give our limits of integration in terms of u, that means we actually don't have to substitute our x's back in. We can just evaluate as soon as we're done integrating, which is really nice. So this is du over 3 and u to the 5th, so we have 1/3 u to the 5th du from our substitution step, x cubed plus 2. And we're going to now integrate in terms of u. So we are going to have 1/3 u to the 6th over 6. And then we are going to be evaluating this from u equals 10 to u equals 3. So now we don't have to plug our x's back in, and that's really nice. So this is 10 to the 6th over 18 minus 3 to the 6th over 18, which works out to be 999,271 over 18. There are no common factors, so this can't be reduced. All right, let's take a look at one more example. Okay, and we're going to, this time we are going to change the limits of integration. Okay, so example 3, we have the integral from 2 to 5 of x minus 3 times radical 6 minus x dx. Okay, so this is another one of those funny ones where we would love to distribute what's under the radical, but it's not a single term, so let's make it a single term. So we have let u equal 6 minus x. So x will equal 6 minus u, and du is going to be negative dx. So let's sub everything in. So we're going to have, and we're also going to change our limits. So our upper limit is 6 minus 5, which is 1, and our lower limit is 6 minus 2, which is 4. So we're integrating from a smaller number, a bigger number, to a smaller number, and that's actually okay. It doesn't matter, it just means we're going to be counting our area backwards. Okay? So now, and it's still gonna work out okay. So now we're gonna rewrite our integral. So our lower limit is 4 and our upper limit is 1. See, I'm keeping these straight. I'm not just putting the smaller one in the bottom. And then I'm gonna replace x with 6 minus u. So I get 6 minus u minus 3. And then 6 minus x is just u, so this is times u to the 1/2 du. And du is negative dx, so I'm going to stick a negative right out in front. Okay, so now we'll simplify this. We're going to expand. So we've got the integral from 4 to 1 of, we have 6 minus 3, so we have 3 minus u. Negative that is u minus 3 times u to the 1/2 du. And then we are going to expand the brackets. So using, of course, our addition rules for exponents, 1/2 plus 1 is 3/2. So we get u to the 3/2 minus 3u to the 1/2 times du. And again, we're not going to have to, we're going to just be able to evaluate this straight away. Integrating, going up, powers go up by 1. So we have u to the 5/2 times 2/5 minus u to the 3/2 times 2 over 3, but the 3 will cancel, over 3 will cancel, so minus 2u to the 3/2. And we are going to be evaluating this from u equals 4 to u equals 1. So we're going to be, u equals 1 is going to go first, and then u equals 4 is going to go second. So we now have some lovely substitution to do in here. We're going to substitute 2 times 1 to the 5/2 over 5 minus 2 times 1 to the 3/2. And then we're going to be subtracting in brackets 2 times 4 to the 5/2 over 5 minus 2 times 4 to the 3/2. And we're going to put a closed bracket there. And then we're going to simplify all of these. So we get 2/5 minus 2 minus, top part is 60, 2 to the 5th is 32, 64/5 minus 2 to the 3rd, 8 minus 16. And so out here, we are going to do the fifths, 2/5 minus 64/5, and then we've got our minus 18. We end up with 70/5 minus, we combine our positive pieces, so we have 16. In fifths, that's positive 80 minus 2 minus 64, so minus another 10/5. We wind up with 8 over 5.